Hi, good afternoon, everybody. Sorry to keep you waiting for a few minutes. I'm told that social distancing isn't required, so I'll get rid of this. Welcome to the second of our webinars on designing closed-loop systems. This will actually apply to closed-loop all systems, not just borehole systems. It's a long time since I've been in the public domain presenting, so apologies if I'm a bit rusty on this. And also, I have been away from the office and from my home for some time now, so I've put this together on the basis of what's on my laptop. It might be a bit rusty around the edges, so apologies if it's not as quite as slick as one might hope. So what I'm going to try and do is why hydraulics. I want to raise the awareness of the significance of the issue, show you why it's important and the impact it has on ground closed loop systems. I'll then take you through a very basic approach to hydraulic design. And what I have to say, principles of what I have to say apply from tiny domestic systems to full-blown megawatt system. Principles apply all the way through. And the audience that I'm probably pitching this to, I'm not sure who out there, the highly experienced closed-loop installers that this won't be news to. I'm really preaching to people who want to be designers, who have been involved in design, but may not be aware of quite the significance of that hydraulics has to these systems. The issue is, you could argue that this is the forgotten part of design of closed loop systems. If you up to this point here, loads pump. This could be an air source heat pump or a ground source heat pump. The unique part about closed loop ground source systems, and even applies to open loop, is this thing here. This pump in the system that you need for a closed loop system is going to consume energy. We're called parasitic energy. So it's additional electrical energy over and above what the heat pump is going to burn. And if that parasitic energy becomes significant, it destroys the performance of the heat pump. So you've paid for an expensive heat pump where the manufacturer has bust a gut over years to gradually improve the COP. You can come along in one fell swoop and not pay attention to the hydraulics, and you will crucify the performance. So it's extremely important that designers get their head around this and that installers appreciate the issue to protect the technology in the sense of protecting its reputation for potential high efficiency. Now, Chris took you through last week in his design exercise of all of the other issues that go around coming up with a design for a closed loop system. And I'm just talking today about this tiny part down here called hydraulics. So taken on board all the significant points that Chris has made, but I am just going to focus on this. And the point being that you can do all this other exercise up here. If you neglect this part here, you undo all the good, potentially undo all the good work that you've done in designing and coming up with the amount of ground loop length, whether that be number of boreholes, number of ground loops in a trench system, or even loops for a closed loop lake system. Some of you know me well will have seen this picture before, and apologies, but this is from the rogues gallery, not the technician. The rogue is the pump. This was discovered by one of our earth energy technicians some years ago in an underground bunker that was, he couldn't understand where the noise was coming from at the bottom of the garden. And this was the pump he found. Now, if you numbers on this, it was for a 50 kilowatt heat pump. So let's say it had a COP of about 4, and the electrical input to that system was 12.5 kilowatts. The pump was rated at 11 kilowatts electrical. So the COP now becomes 50 divided by 12.5 plus 11, a COP of 2.12. So you might as well have sold the customer an air source heat pump. And that's just the first bit of the bad news. The reason someone was calling, you fix it. And the answer is no. It's too late at this point. All that hydraulics impact is in the ground loop that's been installed underground. The only way you could resolve it is dig the whole lot up and start again. And here's another simple example. Chris may have logged this one in. This was a by-the-by that happened to me. I was asked for a quick and dirty sizing on a heat pump while I was in a car somewhere. 12 kilowatt heat pump. I kicked back and said, do 360 meter holes in 32 mil. The pressure drop would have been about 15 kPa, and it would have been a little Wheelo 37 circulating pump. 3 months later, I met up with the client, who was a rep for a manufacturer, and I said, how did it go? And he said, well, the driller turned up and said, forget 3 holes, I'll just do a 180 meter hole with 40 millimeter U-tube. So the pressure drop now is 120 kPa, and the pump size has gone off the graph with a parasitic energy consumption that's just huge. So you completely destroyed any potential efficiency of this system. Again, he might as well have sold an air source heat pump. And these are other things that we have tripped over in the past. Comments from clients or site people, drillers who announce that we, in a fairly macho statement, that we only use 40 millimeter U-tubes, and that we had an operation where we couldn't understand why the holes were being drilled to 100 meters when we'd specified 80. And they had the response that all boreholes are always 100 meters deep, so be wary when you walk into that. This is the graph that actually shows you what's going on in this. So as looking along the bottom here, as the pump power increases as a fraction of the compressor power, you begin to pull down the actual COP. So in this case, going from say nearly 3.5 COP, if you get up to 10% of compressor power, for the pumps, you've pulled that machine down, that system down to a COP of about 3. So this is what we want to attempt to remedy. You want to be somewhere up here where we're a few % of compressor power only is being used to circulate the ground loop. So there's a little bit of basics here on the where and how of ground loop heat transfer, just so you can understand some of the processes that are going on and therefore what we have to address. Where you've got, so we've got a horizontal pipe here, but you could rotate this 90 degrees and it applies to a borehole. So this is a situation where we've got so-called laminar flow in the pipe. Now when you turn the heat pump on and start circulating, the temperature in here drops as the heat pump begins to suck energy out of this closed loop circuit. And as the temperature drops in this fluid here, it's going to induce the flow of heat from the ground into the tube, whether it's a U-tube or tube. The heat has to get through the pipe wall, and it has to get through this boundary layer here, which in a laminar system offers some resistance to the flow of heat. So one way of changing that is you move to a non-laminar. It's not necessarily fully turbulent, but it's non-laminar. The streamlined flow is now being ported, and you've got turbulent flow will reduce the effect of this boundary layer here. It really stirs things up at the pipe wall here and reduces the resistance to the flow of heat into the tube. So this is where closed loop ground source systems tend and try to operate in the serious parts of the system where you're trying to either extract heat from the ground in your heating mode or rejecting heat to the ground in cooling mode. And I'm not going to go in, but the characteristic number that defines whether we're laminar or non-laminar or turbulent is the Reynolds number. We don't have to worry about it too much. It's computed from those factors that I put up there: the density, the velocity, the diameter of the pipe effectively, and the viscosity. And it's a dimensionless number. It doesn't have any units. For the sake of argument here, we can pretty much consider the system to be laminar when it's below 2000 and turbulent when it's above 4000. We can discuss that, but that's to give you some idea of what we're talking about. This graph here tries to illustrate what's going on. Please don't quote me too heavily on this particular graph. It's illustrative more than totally accurate. But what's going on here is the blue line is the pump power that is going up. You see, as the Reynolds number increases here, the pump power required to get the fluid around is growing all the time. So we'd like to be down this side of the graph, but we're laminar down here. And this is the heat transfer that's going on in laminar flow. Now, you can see that as we move slowly towards moving towards being non-laminar and approaching turbulence, there is a significant jump in the heat transfer rate here. And then it curls off a bit and it goes on up. But the trouble is that your pump power is increasing on you all the time. So we want to try and be somewhere here where we pick up the benefit of this jump in heat transfer. Our pump power's gone up a bit, but we haven't gone ballistic with it. So the simple message is that as we increase the Reynolds number, the heat transfer improves, but the pump power goes up. So the challenge for the designer is you've got to try and maximize the heat extraction or rejection for cooling while you minimize the circulating pump power. Now, everything I'm going to try and address now is actually covered in a fairly well hidden document that's on the MCS website. We put it together for designers to use as hydraulics. It's remained fairly cleverly hidden. I'll put the links to these documents at the end of the presentation. So someone wants to go and grab these now, if you get into them, everything that I'm discussing and the principles that apply are covered in there. The first thing you have to do as the designer is to set yourself some kind of design target for what the pump power is going to be. In MCS, it was decided I think it is started as 2.5 to 3% of the thermal output of the heat pump is what your electrical circulating pump power should be. It is then bumped to 3%. I'd actually prefer it to be, you want to be aiming for your electrical pump, your circulating pump, the electrical consumption of that should just be a few percent of the compressor power. So I'd say less than 5%, but try and get it fairly low as you can against the cost implications. Now, in doing the hydraulics, there are some, what we call the pressure drop components, if you like. I've divided those into 4, so I'll show you a diagram in a moment that explains these. There's the active elements, that's where the real heat transfer from and to the ground is coming, all the fluid to your heat pump. You've got the heat pump itself, and then you've got an allowance for contingency and the fittings and the manifolds and the other bits and pieces. This illustrates the notion of the active components. So in the simplest one is on a borehole system, those borehole U-tubes are the active elements. Slinky arrangement, those slinkies are the active elements. And in a standard serpentine trench system, these are the loops in the ground are the active elements. So they're the ones that we need to focus on attempting to maximize the heat transfer out of the ground for minimal pressure drop. And the thick black lines are the header pipe work. We're not interested in maximizing any heat transfer in those, and we can go as slowly as we like in terms of flow rate through there. And the other element in the closed loop system is the pressure drop through your heat pump. So we want to go and compute all of these components and add them together, and that'll give us the total pressure drop in the closed loop system. Now, as a designer, you've effectively got some fixed parameters, so at least something gets bolted down for you. You've selected your heat pump, and the manufacturer will have a minimum heat pump flow rate. You might actually not necessarily fully agree with it, but for a designer's point of view, you probably want to take care that you are going to achieve that minimum heat pump flow rate. Because the first thing a commissioning engineer from the manufacturer might do when he turns up on site is say, you're not hitting the minimum heat pump flow rate, I'm not even going to bother. So bear that in mind, and that's a given for you. There's a starting point. That is what the total flow rate around the system is going to be. The other thing that the heat pump manufacturer will specify very often is what minimum protection, freeze protection they want on the heat pump. It's nominally usually minus 10 C. Some heat pump manufacturers want minus 15. So be alive to that, but that's another given for you. And the other thing that's a given is the pressure drop in the heat pump. There's very little at that minimum heat pump flow rate. You can't do anything about the pressure drop in the heat pump. And I would just, put a warning out. Closed loop ground source heat pumps really should be taking care of. There are heat pumps out there that really have very significant pressure drops on their heat exchangers. And that's going to make it harder for you, because to keep the total system pressure drop down, you're going to have to reduce the pressure drops on the ground loops if you've got a very high pressure drop in the heat pump. And the other given here is that we're going to be designing towards a non-laminar, so a transition zone somewhere between laminar and fully turbulent. And that's going to be a Reynolds number of somewhere of the order of 2,100. It might be 2,400, but it's not going to be less than 221. And then there's some antifreeze issues. We could hold a whole webinar on antifreeze issues, but we're not going to do that today. So you want to be watching out for what's the viscosity of your antifreeze that you want to work at low temperatures. So we might be designing the system to go down to 1, 0, -1, -2, -3. So you want something that is not very gloopy and hard to pump. The concentration of that antifreeze or thermal transfer fluid is determined by what the heat pump manufacturer is asking for in terms of minimum freeze protection. Now, the variables that you've got to play with are, you have already done your design that's given you your total number of meterage. So what Chris took you through will have given you your total meterage of borehole or trench loop or whatever you're using in a closed loop system. You then have got the possibility of playing with the number of boreholes, the number of loops and their length. So the lengths and versus the number. So you might have come up, for example, with just very small system, 100 meter borehole. But is that could equally be from a thermal point of view, that could be 2 50 meter boreholes or 4 25 meter boreholes. So you've now got the opportunity to play. You could play with configuring configurations such as 1 or 2 single or double U-tubes, and you've got all the header arrangements to play with. So size of pipe, you know how far you're going to run from your borehole field, your array field back to the heat pump, but what diameter configuration are you going to use for the headers? I won't go into this in too much depth. In the MCS document, there is the 3 spreadsheet flow charts in there that give you the basics of how you go through this exercise. So you've got your heat pump thermal output. Are you going to use, well, hopefully today you are going to use a high efficiency circulating pump. That will tell you how much pressure drop you've got to play with. So you look up your heat pump pressure drop that's given to you by your heat pump manufacturer. Then you go and do a computation on your active element. And remember, where you've got parallel loops of boreholes or parallel loops of skids or serpentine loops, you only have to compute the pressure drop in one of those loops. You don't add them all together. You use a pressure drop tool or spreadsheet to do it, to actually compute the pressure drop in your loop, in that one loop, at your given flow rate with your antifreeze. So you then add these 3 elements together. You will add your active element, your header element, and your heat pump pressure drop. And we tend to then lob in an allowance for contingency and the extra fittings, a nominal figure of 15%. If you're really keen, you can go and work all of those out and add them in as well. And then you check whether your total pressure drop is less than your permitted pressure drop. Otherwise, you've got to go around the system again. And so this is the flow chart for how to do active elements. So you're looking up your flow rate. You're going to select your heat pump flow rate. You select the antifreeze you're going to use and its protection level. That'll give you the concentration of the antifreeze. You select the pipe that you're going to use. So are you going to use, let's say, domestic boreholes, might be 25 mil OD or 32 mil or possibly 40. So you're going to take a stab at using one of them. You divide the flow rate by the total number of loops that you're proposing to use, and they'll get you the flow rate in your loop. You go and use your calculator or the chart that I'm about to show you. And you pick up the pressure drop in that, let me see if I can get one of these up. So these are ready prepared charts that are in the documents I referred to that, for example, are set up for 25 millimeter SDR11, 32 mil, and 4 mil SDR11. This is flow rate down the bottom. So the flow rate in your U-tube or your loop, and this is set up for a concentration of ethylene glycol protecting down to -10C. And so you stick in here, you decide you're going to use 40 mil pipe at 0.6 liters a second. You go up here and come across, and this will tell you the pressure drop per meter. Now you can either use these charts, which are pre-prepared for you, or a spreadsheet of some sort that computes these numbers. So that will give you the active element pressure drop. And it's sorted out for you that if you're down in here, this will be laminar, and you don't really want to be there. So you've got to have another go and make sure that you are living in the right segment of these charts. And then you do the same exercise for your header pipe work. And the charts are provided for the larger diameter pipe work, so it covers up to 93, 90 millimeter pipe work. So go through, there you go, same exercise. You might be using 63 mil or 90 mil, let's say. You pick off your pressure drops per meter on here and work out your total pressure drop in the header. Or these charts, they're a bit limited. They were specifically designed for MCS. They will probably cover, they cover all MCS size domestic systems, but you could look out for a calculator where you provide the pipe diameter, the flow rate, the length, and your viscosity of your antifreeze. And remember, this is going to be the viscosity under your worst conditions. So let's say under MCS, where you're designing at 0 centigrade, you're entering water temperature. You've got to use the viscosity that will be that fluid will have at that temperature. And then the calculator will give you your Reynolds number, what the pressure drop is, and if it's turbulent, and the laminar pressure drop if it's laminar. So I've got a very simple example here, and don't hang me too much on the actual numbers, but it tries to illustrate the exercise. So let's say we've got a 20 kilowatt heat pump. The flow rate will be nominally about 0.95 litres a second. So you use your design tool or the MCS tables maybe with Chris's caveats applied, and you get your attempt at the boreholes at a given depth, the number and the layout. So this is going to come back with the total meterage of active elements that you need. And let's say it's come back saying 6 holes, 67 meters deep. So we're coming up with a 400 meters of hole. Well, what's going to be the best way to lay these holes out? What depth and layout of depth and number of holes is going to be best from the hydraulics point of view? So taking those, we use the calculator or the charts, and we use the 3 common pipe sizes there. We get those Reynolds numbers and those pressure drops. So the 25 mil has got quite a high Reynolds number and a pressure drop of 36 kilopascals, about 3.6 meters. 32 still has a Reynolds number that's usable and a pressure drop of 11 kPa. But the guys who insist that they're always going to use 40 mil U-tubes are now in trouble, because the Reynolds number has fallen to 1700, although we've got an immensely low pressure drop. But we're not going to be getting the heat transfer out of those U-tubes with a Reynolds number down here. So then we go. So those are the numbers we've come up with in the first stab at this, and here we're going to have a second go. So we're now changed. We've got to end up with approximately the same total borehole meterage. So in 25 mil, we now change this to 7 holes from the 6, which will be 57 meters deep. The flow rate will have changed in each U-tube because we now have 7 holes, not 6. New Reynolds number of 2000, a pressure drop of 23. But that's higher than what we had for the 32 mil. We had a usable Reynolds number, but we had a lower pressure drop. And if we redo the 40 mil U-tube, so we could now have 5 holes of 80 meters, it's still the same 400 meters total. The flow rate will have gone up, which will attempt to bump the Reynolds number. But this is a bit marginal, this Reynolds number. So we're probably coming back to the fact that this will be the 32 mils, 6 holes at 67 meters is probably the optimal solution for this design. And what you would need to do then is repeat your borehole, your sizing calculations. You'd go back to GLEPro or EED or the tables and repeat the exercise to hone in on the correct total borehole depth given your loop length, given whatever spacing you're assuming and what space you've got to play with. So here we'd have worked out the balls were about 12 kPa, the headers were 25. Let's say we haven't done that, but let's assume that's maybe what they are given the distance from. You get to 27 kPa, allow 15% for the headers and for the fittings and bends in the plant room and so on. Now we've got a total that's less than 50 kPa. We had to add in the heat pump pressure drop, and so we've got a total here of 40 kPa at 0.95 litres a second, which is very livable with. And you go away and select a pump on that basis. That's summarising what you go with, the pump you're going to go and look for. And so you want something that's going to sit here. This is your pump performance curve, and this is your ground loop hydraulic performance, and where they interact is where your pump is going to sit. You go to a manufacturer's chart, you're going to want to pick a pump that sits comfortably. This is a 3-speed pump, fixed speeds. You want to select a pump that's hopefully not right up here on the edge of it, but somewhere down here. And that's your job done. I've just lobbed this one in here. This is an example, just to clarify, this is an example of a manifolded set of boreholes, 5 holes in a trench, say, that come back to a manifold. When you're computing the active, the pressure drop in the active elements, you take this one, you'd work it out for the longest loop in total, right? And don't blow it on that. This is just an example of what could go horribly wrong if you're not careful. The borehole field is up over here to the right, quite a bit. This is quite a big commercial, non-domestic borehole field. There were then 300 meters to the plant room. So you've got a total run in the headers of 600 meters. Now there's no great big problem with that, but you need to be making sure that that header pipe work is of a sufficiently large diameter such that you don't create a huge pressure drop and a huge parasitic pumping energy. The council system was going to be paying something in excess of £16,000 additional electrical consumption, unless the header pipes were bumped up in size. So don't throw away all your good borehole design work, then all your active element design work and suddenly throw it away in the header design. Well, remember, the big issue here is that in other forums, we're saying you're going to put these systems in for 50 to 100 years. So any parasitic energy that's running for, say, 2,000 to 4,000 hours a year for 50 years is bad news in terms of energy and carbon and running cost. Another area, as well as not blowing it on the headers, don't blow it on the manifold. So you want to be using the properly designed ground loop manifolds. In the past, we have tripped in, it's not an issue. The pressure drops in those headers for underfloor heating are not a big deal. Pressure drops in manifolds for big ground loop systems, or even small ones, are bad news. So this is, sorry, slightly out of focus picture of a domestic one. And when you get to the bigger ones, these are the sorts of things you need to be looking at and using to make sure that you haven't got an unholy pressure drop in these manifolds. Last area is that we're blessed these days with the big improvement in the technology in pumps. So there are, just make the distinction that there are, when the variable speed pumps came into vogue, they also came with new high efficiency motors, basically. And we're interested in both of them. Where you're after the variable speed, then yes, pick the new high energy variable speed pumps. Make use of the high efficiency technology. And just to warn you that something we're tripping over is that the basic variable speed pumps don't put them on a ground loop. You need to be setting them at a fixed speed, because what they will be doing is controlling on pressure. And as the ground gets colder, and your antifreeze begins to thicken up. You actually need more pump power to keep your flow rate up. These systems, the systems that control on pressure, will actually be backing the pump off and reducing your flow rate in the ground, and everything's suddenly getting worse on you. So be aware of that. We tripped over these where we find these in manufacturers' systems, and they need to be set up on the fixed speed to deliver the flow rate that the heat pump requires. And just the last element here is some of you may have been approached or seen these miracle nanofluids being touted around. These may have potential application on the load side. I don't want to get into it at the moment, but don't be tempted to use these on ground loops. As far as we can see at the moment, if you add these systems, they seriously impact the viscosity of the ground loop fluids. And you won't get any benefit, in fact. There's the link to the guide, the hydraulics design guide materials. If you want to go and check those out, you should find most of what I've said in there. And with any luck, we can avoid any of these. Thanks very much for your attention. I think Chris is lined up to field any questions that you might have been lobbing in.
Thanks so much indeed, Robin. Yeah, we've had a few questions come in, and I'll keep an eye for more coming in as we go. So the first one, Robert Carter asked, do you have data to show the effect of turbulence? And I think you covered that in one of your slides, but perhaps you might want to say a few more words.
Yeah,
oh, sorry.
It is.
Was it me you were asking?
Well, it was me who was asking. Can you hear
yeah,
me?
yeah, I can hear you. Yeah, I was asking you, Robin.
A classic question on conference calls. Can you hear me? Well, there is the slide. There was the slide in the middle that shows the qualitative aspect of that. As you go through the transition, you do see that that jump in the heat transfer. Now, there is an area, very happy to have an offline discussion with people. You could argue that you could use laminar systems, but you will need a lot more loop length. And the reason that the ground source industry has moved to live in the semi-turbulent, the non-laminar transition region, is that boreholes are pretty expensive. And that's where the practice has become, that we want to live in the non-laminar semi-turbulent region. Otherwise, you're going to be drilling immense lengths of boreholes to get the same thermal output. But for horizontal systems, if you've got unlimited access to JCBs or trenches or whatever, then you could design on a laminar basis. Bear in mind that you take account of the hydraulics.
What I was actually wondering was, is there any either empirical or theoretical analysis of the effect of laminar versus turbulent flow? Because it seems to me, yeah, that the surface resistance may be reduced a bit when there's turbulent flow, but I've not seen any data. I've not seen any calculations on it. And for typically as well, when you have laminar flow, your transit rate is going to be less, so your contact time is going to be greater. My calculation and analysis seems to suggest that there would be very, very little difference between the two, but I've never seen any data on it, or anybody with any theoretical thing that I could look to say yes, that is correct. The whole thing seems to be built on hearsay rather than theoretical data.
Well, there is a pretty heavy body of theoretical work in other industries showing the basis of increased heat transfer. But I suggest, if you'd like to get in touch with us offline, with me offline, send it to that email address there. We'll try and provide you with the work that we came up with that is illustrated in that slide.
And I think I could add to that, Robin, by saying there's quite a bit of qualitative work done back in time at Oklahoma State University on this. So there is actually some practical data to back up the theoretical work. And Andy's just said that on the chat, so thank you very much indeed, Andy Howley. Steve Kavanagh was the professor who did lots of that work over there. Can I move on to an analogous question from Craig Baker? Do barreled ground loop pipes increase the Reynolds number and provide benefit to efficiencies?
Do what, sorry?
Do barreled or rifled ground loop pipes increase Reynolds number and provide benefit to efficiencies?
Well, arguably, yes, a bit. I have seen, I mean, that I don't know how many companies are offering them, but Movitech actually have a paper out, a technical paper out, in which they attempt to demonstrate the improvement. I mean, the trade-off that you've got is that you possibly get some increased heat transfer due to the rifling, but there will be a trade-off against some increased pressure drop due to the rifling. But there are some other factors also going on, because they have effectively reduced the pipe wall thickness of the tubes as well. So it's a slightly woolly answer, but I think the manufacturers have provided some technical literature on the claimed improvement. I have used them on a site, but I think it's quite difficult to find the occasions on which they are a benefit. More interest to some extent, same manufacturer or one of those manufacturers is the first manufacturer to move away from standard pipe dimensions. So you now have a 45mm offering, and that can actually be a more attractive solution than the issue of increased performance due to the rifling. It's very brave of them to move away. I mean, the 45mm pipes actually offer you a solution between single and double U tubes, for example.
Excellent, Robin. Thanks very much indeed. We certainly find 45mm pipe very useful when we're drilling deeper, because we're addressing some city centre sites which are congested. Laura's asked a couple of questions, Robin. So MIS 3005 refers to MCS projects only, so sub 45 kilowatts. What about heat pump projects above that? Can the rules be applied just as well, so that it forces designers and drillers to work to similar rules? And then the second, well, I'll answer that one first, Robin, and I'll come back with a second question from Robin. From Laura.
Yes,
sorry.
I'm not sure. Calling them rules is a bit interesting. The guidance provided in those documents applies for a 4 kilowatt system to a 4 megawatt system, and it's making sure that somebody is taking care of this and addressing it. You know, people get their heads around the clever stuff, which is they go and get their heads around running Glee Pro or EED or the other codes out there, and come up with the thermal sizing, and then don't address that.
It's interesting you should say that, Robin, because I spend more time on the hydraulics of a system when I'm designing them than any other part.
Yeah, absolutely. I don't. And as you know, when you get into the fancier systems, such as shared loops and stuff like that, the hydraulics actually get quite demanding and quite complex. So it's just checking that there is somebody in the design side of these systems and that is taking care of this. And you, sorry, Laura, just going back a bit. On the domestic side, where heat pumps are being supplied with onboard pumps, someone needs to be taking care of what is the ground loop that they're fitting to that. You can't make the assumption that any old ground loop fitted to that onboard pump will have low parasitic energy. But yeah, if you follow the guidelines in the design documents, you know, and head yourself a design target of having few percent of electrical consumption in the circulating pumps, few percent of the compressor power, then you should be in good shape.
Excellent, Robin. So I've got a question coming from Peter McAvoy, which builds on what you've just been talking about. So heat pumps with circulation pumps already integrated inside the heat pump. Does this comprise achieving the most efficient system, or has the manufacturer spec'd this okay for the heat pump stroke output expected, without considering, I'm paraphrasing, loop design?
Well, what they've done is they've fitted a heat pump. I mean, what they usually come up with these days is they provide you with the maximum pressure drop, that the maximum external pressure drop that heat pump can support. In other words, that the onboard pump in that unit will support. What you then need to be doing is not necessarily moving to the maximum. You want to move to somewhere that's a few percent of the electrical consumption is your objective. And if you like that example in the talk of the 12 kilowatt system, that could have been a 12 kilowatt heat pump with an onboard pump that would have just totally failed to operate. It wouldn't have even been able to achieve the pressure drop on the 180 meter deep borehole. So they believe that the amount of available pressure drop they are giving you is enough for you to deliver a working ground loop. Your job in life will be to try to minimize the amount of that pressure drop that you need to use. It's an engineering trade-off. It's cost versus efficiency.
Absolutely, Robin. Thanks very much indeed. So Laura just made a comment on the drawing of your boreholes connecting to your manifold, and she asked, would you use a reverse return to link boreholes rather than pipes, and having the problem with longer runs and shorter runs?
Well, and then about my views on here, I mean, I go back as far as Chris on this. Reverse returns were a pretty standard way of doing things, particularly in the US and Canada. And I put my hand up. Our early systems, our early non-domestic systems, made use of them, and I thought I was being very clever designing these reverse return or Tiekelman. They're called Tiekelman systems in Europe. In Europe, we have tended to move away from them. I just flag up, there are some issues about vulnerability and ability. On a reverse return system, if you get a leak in one of the legs of your reverse return, you shut down that array until you can go and sort out the leak. And so they're somewhat vulnerable. You've got to have very high quality control on your installations. In Europe, it's a much more common practice, it's pretty much standard practice these days, that we use manifolded systems. And what would happen is, although you've got different pressure drops in the example I gave you there, so the pressure drop into the borehole nearest the manifold is lower than the pressure drop to the furthest. You design on the furthest, and you have flow balancing valves that will be equalizing the pressure drops in all the boreholes. I'm very happy to have a separate discussion about this, but my advice today would be aiming for a manifolded systems. We actually see combinations of where the borehole, an array of boreholes will be manifolded, and then if we've got multiple sets of those, we might reverse return the connections to the manifolds, because that makes quite a lot of sense, and you're not as exposed there to failure.
The other one I've used, Robin, is exactly the same, but the other way around, using reverse returns to group a few boreholes together and then manifolding that, so you're designing in an amount of resilience that you're comfortable with. Thanks, Robin. That's super. Tony and Bill Harvey have asked, I wanted to see the design guide, but it's only available to members. Perhaps we could follow up with that one, Tony and Bill Harvey. Perhaps you could email info@gshp.org.uk and we can sort out the admin.
Chris, just to clarify, the design guide I'm talking about is on the MCS website. When I'm not talking about GSHPA design guides, there may be some confusion there. As far as I know, I'm not an MCS member anymore. I was able to go on that site and download the hydraulics guides. They have made a bit of a mangling of them in converting them to the new formats, but if anybody's desperate, come through and I'll produce the original documents.
A question from David Reed. In your example of the 40mm Reynolds number being just over 2000, yeah, and you mentioned that was too marginal, yeah, would you set that as a cutoff, or a relatively small change could make a big change in Reynolds number?
Well, it's actually quite interesting trying to rustle up a simple example remotely. I was trying to illustrate what you're trying to do, and I would probably be rejigging that to come up with, say, 2,400, 2,000 target. I was just trying to illustrate the swings and roundabouts that go on as you change your and so on. So you get the principle of it.
Thanks very much, Robin. Type questions. So is there, from Robert Carter, is there any information on expansion vessel sizing to do with the water having its highest density around 4 or 5 degrees? Will pipe expansion be enough to compensate, or are pressure vessels needed? And is there any theory on this?
Sorry, I think I missed a part of it, but this was to do with expansion in the pipe loops.
Are expansion vessels needed on ground loops, or does the pipe expand enough to deal with it?
Probably the sanest answer to give is that put an expansion vessel on. Strictly speaking, very small domestic systems, the expansion of the plastic pipe work can be used to take care of that. So on small systems, you can pressurize the ground loop adequately, and it will always maintain enough pressure to provide the back pressure on the pump. But on bigger systems, as you get into bigger systems, yes, you end up with an expansion vessel.
Can I just add to that, Robin, by saying that be very aware, or make the manufacturer of your expansion vessel, and particularly dosing, automatic dosing equipment, aware of the application and the temperatures involved in ground loops, because a standard offering can often get quite confused by what's going on and cause you more problems than it would help. Andy Howley's very helpfully posted how to Google for the MCS hydraulic design guide. And he's also commented the expansion vessel functions in reverse to steel pipe systems as the pipe expands faster than the fluid. So be aware of this too. You're absolutely right, Andy. You've got to know what you're doing when you're specifying expansion vessels. And it's true really on anything that's bigger than a domestic. One final question, which is an interesting one from Craig Baker. How do installers learn more about shared ground loops on their design?
Well, perhaps maybe Chris could answer that one. We could both answer it probably.
Go on, you first, Robin.
Well, I'm not sure there's anywhere you can go. You're probably not going to find a document on it. This is acquired knowledge. But what I would say is, everything that I've talked about today, you can apply to shared loop systems. To just track your way between wherever the heat pump is and your ground loop, and make sure that the pumps, the combined effort of the pumps and the individual heat pumps is going to be enough under the worst case conditions to circulate in the active elements. To get your Reynolds number where you want it to be, and to get enough flow rate through the heat pump. It is something to be, you do need to get your heads around the fact that, you know, when two, three, 4 heat pumps come on, switch on onto a shared loop, they have to be capable of each individual pump has to be capable of working against the combined efforts of all those other pumps that are running at the time. If that doesn't ring a bell with you, then, you know, get in touch with us and we could explain it. But you've got to recognize that under the worst case, let's say all your heat pumps are running, so all your onboard pumps or your ground loop circulating pumps are running, they have to be able to contend with the total flow rate being pushed through the system by all those other heat pumps.
Well, technically, I completely agree, Robin. That's absolutely fine. There's a lot of intellectual property being developed around the industry by people like myself and Robin. I design shared arrays most commonly, actually, at the moment. And obviously, we wouldn't be entirely willing just to let that go into the marketplace. But Robin's hit the nail on the head as far as all the bases you need to cover. What I would say is, unless you're very experienced, I would probably ask somebody to do it for you, because it's a surefire way of denting your PI cover, unless you really understand all the implications that Robin's outlined there. I think we've run on longer than any other session we've. It's fantastic because of the level of interesting questions that have come in. So there's no other questions coming in. So can I just thank you, Robin, for a fascinating session today, and thank the audience for their excellent questions. And we very much look forward to next week's session, when John Findlay will be looking in more detail at the geological considerations and the installation considerations for closed loop systems. Any final words from you, Robin?
No, just thank you for everybody for signing in and joining in, and I hope you found it reasonably useful.
Excellent. Well, thank you very much indeed, all. Have a great day.